Welcome to this explainer. Today, we're diving into an absolute masterclass in robotic software integration. We're tearing down OtoNav, which is this incredible end-to-end ROS2 and MuJoCo pipeline built specifically for robotics engineers. Look, if you're tired of flaky tests, mysterious integration bugs, and that heart-stopping fear you get right before deploying to broken hardware, you are definitely in the right place. We're going to explore exactly how a meticulously crafted software-in-the-loop, or SIL, platform can completely transform the way you ship robotics code. Okay, let's dive right in. We've got 6 key architectural pillars to tear down today. We're going to cover infrastructure first, the sim-to-real how boundary, deterministic sim time, the 4-layer test pyramid, merge queues, and finally, we'll look at 6 real-world bugs this pipeline causes. First up, we're looking at infrastructure over algorithms, or basically understanding the true cost of robotics. I absolutely love this quote from the source material. It says, "Simple robot plus bulletproof pipeline beats sophisticated robot plus failing pipeline every time." Man, that hits hard, doesn't it? Because we all know that shared, agonizing pain of bricking a real, highly expensive rig just because some algorithm that worked flawlessly on their laptop simply wasn't ready for the real world. A brilliant algorithm that you can't reliably ship? That's not an asset, that's a liability. The real cost in robotics is always in the integration, the testing, and bridging that massive gap between a developer's bench and a production robot. I mean, let's just think about these common team pain points for a second. I'm sure you've felt these. Your code passes perfectly in simulation, but then the physical robot veers straight into a wall. Or a pull request is totally green on your feature branch, but the second it merges, bam, it breaks main. Then there are tests that are incredibly flaky just because they rely on unpredictable wall clock timing. Or, my personal favorite, the classic works on my machine gap, where your local Ubuntu setup has completely different binaries than the production Docker image. These aren't just rare edge cases. For a lot of teams, this is the default experience, and it's exactly why the OtoNav platform was built, to structurally eliminate these exact failure modes. Moving on to Pillar 2, the sim-to-real hail boundary, which is really all about building that perfect seam in your software. So the really crucial point here is this hardware abstraction layer, or HAL, boundary. Inside OtoNav, this is implemented as a single abstract C++ class called the Robot Hardware Interface. And what it does is it completely separates the ROS environment from the MuJoCo simulator. The golden rule here is that your control and navigation code must never, ever touch simulator types. You can think of this boundary as the load-bearing wall of the entire sim-to-real system. It keeps your core logic completely agnostic as to whether it's navigating a virtual world or the physical one. This setup becomes incredibly clear when we look at the actual implementations. On one side, you have the MuJoCo interface, which is used exclusively for your software-in-the-loop testing in CI. On the other side, you have the CAN bus interface, which is the hardware stub just waiting for physical deployment. Going from sim to real is literally just swapping out these two backends. The entire raw stack sitting above them, the kinematics, the navigation, all your controllers, it remains byte identical. Basically, if a hardware change ever forces you to alter your core navigation code, well, your HAL has failed its job. All right, Pillar 3 is an absolute game changer. Deterministic CI via sim time. This is how we kill the flake. If you've ever had a test fail in CI that just passed locally on your own machine, you know the absolute nightmare of wall clock time. GitHub Actions runners have wildly unpredictable CPU loads. Think about it. If you write a test that sleeps for 2 real seconds to wait for a node to spin up, a slow runner might actually take 3 seconds, and boom, your test falsely fails. Sim time, on the other hand, is driven entirely by the simulator tick. It only advances exactly as fast as the physics step is called, making it completely deterministic. A test that says reach the goal in 5 seconds means 5 seconds of simulated physics. It literally doesn't matter if the host CPU takes 8 seconds or 40 seconds to calculate it. Here's how OtoNav actually pulls this off structurally. The bridge node publishes to the /clock topic, and that's driven by a wall timer. Crucially, though, the bridge itself lives in wall time, so it doesn't accidentally deadlock waiting for a clock it's supposed to produce. Meanwhile, every other node in the system runs with use sim time set to true. The tests themselves use conditional waits, no wall clock sleeps allowed ever, and they assert against a very strict sim time budget. This entirely removes all that network and CPU non-determinism from your integration tests. It's brilliant. Which brings us to Pillar 4, the 4-layer test pyramid, acting as your fail-fast filter. 45, that is the total number of tests run on every single pull request in this platform. And the best part, it all happens in under 10 minutes. A massive takeaway for us here is that rigorous production-grade CI does not have to be slow, not if you aggressively cache your builds and actually layer your tests correctly. So let's step through this 4-layer fail-fast filter. Step 1 is linters and formatters, because honestly, missing a new line in your YAML file shouldn't cost you 20 seconds of sim time to discover, right? Step 2 is gtest unit tests. These are testing pure math functions completely isolated from ROS nodes, so they run in milliseconds. Step 3 is a Python smoke test. This just ensures all the topics come up properly and catches any silent quality of service mismatches. And finally, Step 4, the full SIL acceptance scenario. This is where it actually spawns the simulated robot, gives it a goal, and asserts that it navigates perfectly without hitting any virtual obstacles. Next up, Pillar 5, merge queues to protect main. This is how OtoNav solves the classic integration problem. Let's just walk through this timeline together to see how GitHub's native merge queue fundamentally solves that awful passed on my branch, broke on main issue. So you open a PR and it's tested against the base branch. All good. But when someone approves it, it doesn't just merge right away. It goes into the merge queue. The queue then takes your PR, pulls the absolute latest version of the main branch, and retests your code against that future integration state. Only if that passes does it actually merge. Basically, the queue acts like an automated integration engineer, serializing your PRs and making sure main is never, ever broken by overlapping merges. And to really enforce this, the pipeline applies some strict structural rules. It requires squash merges, so you get exactly one clean commit per PR on main, creating a perfectly bisectable history. Plus, it requires all green status checks. Every single check must pass. You literally cannot bypass the pipeline by accident or even by force. And that brings us to pillar number 6, the bugs actually caught by SIL. Let's look at some empirical proof. Look, a test suite is really only as good as the bugs it catches. So here are 3 real-world examples that this exact pipeline trapped. First, there was a silent QoS mismatch caught by the Layer 2 smoke test. A reliable subscriber was listening to a best effort publisher. Now, in ROS2 DDS, that's an incompatible combination that throws absolutely 0 errors. It just silently drops all the messages. Yikes. Second, the pitch bug caught by the Layer 3 SIL test. This was caused by a wild physics and algorithm interaction. And third, a missing Docker copy command caught right during the release build, where the container actually silently built without the navigation package entirely. I really want to emphasize this. Standard isolated unit tests alone would have completely missed every single one of these bugs. The pitch bug is just this perfect little mini story of why we go to all this trouble. So during the SIL acceptance scenario, the robot kept stopping way short of its goal, basically claiming there was an obstacle that just didn't exist. By downloading the ROSBag artifact from the failed CI run, the developer saw exactly what happened. On forward acceleration, the 2-wheeled robot pitched nose down. This tilted the front LiDAR beams directly into the ground, so the obstacle guard read the ground as a wall and triggered a false stop. The crazy part? The guard logic was correct. The controller was correct. It was the dynamic interaction between physics and software. The fix required adding a front caster wheel and tuning up the velocity feedback gain so the nose wouldn't dive. Testing physics and algorithms together in SIL is simply non-negotiable if you actually want to catch these things. And finally, we have to remember that all of this testing only matters if you actually deploy the exact thing you tested. Test what you ship. The release runner image that physically goes onto the robot is built from the exact same ROS base layer as the CI container. When a tag is pushed, it gets stamped with a commit SHA. So when someone on the floor asks, hey, what code is running on this robot right now? You have full end-to-end traceability right back to the exact environment tested in CI. I'll leave you with this final, somewhat provocative thought to conclude our explainer today. Think about it. If your robotics tests don't run in deterministic sim time, are you really testing your code? Or are you just testing your CI runner's CPU load? Rethinking your infrastructure from the ground up to prioritize this kind of robust, bulletproof integration might honestly be the best investment your robotics team ever makes. Thanks so much for joining me to break down this amazing OtoNav source material. And hey, keep building those bulletproof pipelines.